So this will be the third and final lesson for Unit 2, titled Differentiability, which for us is going to mean the ability to evaluate a derivative, which, if you recall from the last lesson, everything came down to talking about this limit definition for the derivative and having you evaluate the derivative function. And this lesson is then going to carry us into some of the implications and applications of those derivative functions. So what I'd like you to do first is take a look at the graph that is shown of this function, this blue line right here. And what I'd like you to do is go ahead and use your knowledge of algebra and write down the equation for that line on line number 1 right here. Go ahead and pause the video and do that now. And what I would assume you came up with was the equation y equals 2x plus 1, which would be a good guess, but it's not the line that I graphed. And I'll be honest with you, that's because I tricked you a little bit. I didn't give you any sort of scale for the grid on this graph, and you had to assume that each box represented 1. You correctly assumed that the slope was up 2 over 1, but what I'm going to tell you now is that every box is actually 0.001. It's not a full unit. With that in mind, what I'd like you to do is go ahead, pause the video once again, and write down the equation for the line you see, knowing what the scaling on the graph is equal to. Go ahead and pause now. Okay, so now that you know the scaling, what you probably came up with was, well, the slope's not going to change, but my y-intercept is now going to be 0.001. And I'll tell you that's 100% correct for what you see on the graph, but that is not the function that is shown here. The function shown here is actually sine of 2x plus 0.001. Now, with your knowledge of functions, what you might be thinking is, well, shouldn't a sine graph look something like this? And yeah, it should, and I'm going to tell you it actually does. The issue is, this is the same graph, but zoomed in so closely that you can't even tell that there is a curve. And I'll prove that to you now. I have already graphed the line that you saw on your notes. I've graphed it on Desmos. What I'm going to start doing is zooming back. Zooming back out. You see that scale get larger and larger. Still looks like a line at this point. Still looking like a line as I zoom out, and now it starts to look like that sine curve that we are used to seeing. It's no trick, this is the same exact function, and as I zoom in farther and farther, you can see it takes on this property that it looks like a nice straight line. What does this mean for us? Well, what this means is something that we talked about in the last section. What you're actually seeing is this line 2x plus 0.001. But what that actually represents is the tangent line to this curve at x equals 0. And this is a basic property of derivatives. And it's the idea of differentiability. Differentiability means that the derivative exists for each point in the domain. And what we just saw in our example is when you zoom in, the graph looks like a nice straight line, what we call local linearity. If a function has a derivative, you will see a straight line at that point. Granted, you may have to zoom in pretty far like we saw in our example, but that is what we should be seeing for any function where the derivative exists. And what that allows us to talk about are places where the derivative does not exist, or what we're going to say is where it's not differentiable. And places where it's not going to exist, the first one is a cusp or a corner, any sharp turn. What a cusp looks like is maybe something where you start off with a nice straight line, and at a certain point, you change to a curve. A corner, well, that could be something like our absolute value function, where we know it makes this nice V shape. But in both of those examples, those places where you make the sharp turn, no matter what you do, you can't zoom in and see a line. You will always see that corner there, which means we cannot describe the equation of the tangent line at those points. The second place that we'd have an issue where the derivative would not exist are any of our discontinuities. So if we have a hole in the graph, if we have a vertical asymptote, if we have any sort of jump. If you're going to make a tangent line, you need a point to exist for that tangent line to intersect. And if the point does not exist in the domain, we cannot possibly have a tangent line to intersect our graph. And the last one's the rarest one, but still something we want to keep in the back of our mind, is any graph where we would have a vertical tangent. Now the most common example is a cube root graph, which looks something like this. And on that graph, there's a point where the graph turns, and for a moment in time goes completely vertical. And from our algebra knowledge, we know any spot that could be modeled with a vertical line has a slope that is undefined. Or for us, that would mean that our derivative is undefined. So let's take a look at some of the implications of these places where our functions would not be differentiable. And we're going to do this in two true or false statements. The first one, differentiability implies continuity. Well, if I can zoom into a function and see a nice straight line, even if that function is a curve like we saw in our earlier example, if I see a nice smooth connected line, then that would imply that I am continuous at whatever point I might be dealing with. That's a true statement. Now, take the same idea but reverse the statement. Continuity implies differentiability. Well, think about an absolute value graph. Let's say we've zoomed in on this point right here with a corner. It's definitely continuous there, but it's not a line no matter how much I zoom in. This is a spot where I could be continuous but not differentiable. Since it fails for this one type of function, I cannot say that that statement is true all the time. Sometimes it will be, sometimes it won't be. Even our spot like on a cube root graph where I go completely vertical at this point, definitely continuous there, but not differentiable. What we're going to do now is take a look at one of the big applications for differentiability. And it's going to be our second big theorem. And if you remember, our first big theorem was the intermediate value theorem, which was an application for continuity. And that one allowed us to prove the existence of certain function values. Well, what the mean value theorem states is that if a function f is differentiable and thereby continuous over the interval a to b, maybe something like this function here, then there exists a point x equals c within that open interval where the instantaneous rate of change equals the average rate of change. Or, put in the proper notation, our instantaneous rate of change at c, which would be f prime of c, equals the average rate of change over the interval, f of b minus f of a, all over b minus a. And what you need to recall for this to make sense is that when we talked about average rate of change, we were talking about the slope between any 2 points on a curve, ignoring what happens in between those 2 points. We can see this function decreases then increases, but the average rate of change imagines that we connect them with a straight line. What the mean value theorem states, at least one point C, we can draw in a tangent line with the same slope. They would be parallel. And so just like how the intermediate value theorem allowed us to prove the existence of function values, this is a property of differentiability, allow us to prove that certain slopes exist along a curve. And so let's take a look at this in practice. Given f of x and f prime of x, a function and its derivative, find a value c that satisfies the mean value theorem. So looking at our function, we have f of x equals negative 2x squared plus 16x minus 26 on the interval from 4 to 6. And to give you an idea of what that looks like, I have already graphed that function, and I'm going to drag it over to our screen. And on that graph, here is x equals 4, and here is x equals 6. What the mean value theorem is saying is that first I'm going to look at the average rate of change between these 2 points. F of 6 minus f of 4 all over 6 minus 4. Now I'm going to write this whole thing out, so that's going to take a little bit of time, but again, remember, these calculations are things that go ahead, pop them right into a calculator. Don't worry about wasting a lot of time with writing these things out or proving what the values actually are. And I'll go ahead and tell you that it is going to be negative 2. And is the slope between these 2 points equals negative 2, definitely decreasing, so that value makes some sense to us. What the mean value theorem states is that since this function is differentiable, at some point at that c value we're talking about, f prime of that c value is going to equal negative 2. We're trying to find some point in the middle where that happens. So we're trying to find some point where, taking our derivative and plugging in c, negative 4c plus 16 equals negative 2. And that c value would be 9/2 or 4.5. Locating that value on the graph, which is right about here, I'm going to go ahead and draw in the tangent line there. Even though my tangent line doesn't look perfect, it sure seems that this also has a slope equal to negative 2, the same as the average rate of change. And that's the idea behind the mean value theorem, is that based on the properties of differentiability, for any differentiable function, you can find a point where the average rate of change and the instant rate of change are exactly the same. And moving right along, the last two things we're going to look at, one is going to be another application for differentiability, but the one before that is going to be a useful tool that you're going to need to be familiar with throughout the remainder of this course. And that is derivatives and using your calculator. So being able to use your calculator to find the value of the derivative at a particular point. And so the example that I've put up is f prime of 0.57 if your function looks like this, x cubed over the natural log of x. Now we might be able to find that derivative like this, but you can probably tell that's going to be pretty complicated. It's got a natural log in it, it's a fraction. That's going to be a tough one for us to work through. Well, the idea is at certain points, we don't care about actually finding the derivative function. Sometimes we only care about what this final output's going to be because that's going to give us some important information about the function's behavior. So fortunately, our calculator has a tool built in to help us with that. If you're using any TI calculator, how you get to finding the numerical derivative is by pressing math and then the number 8. So math 8. And notice what it brings up. It brings up this picture here. It says d over d and then a blank that is blinking right now. Well, we're going to fill that in with an x. Inside the parentheses, we are going to input our function. In our case, x cubed over natural log of x. Another thing I want you to be familiar with, alpha y equals will give you a fraction written vertically, which just helps make things a little bit neater. So alpha y equals enter. That allows me to put an x cubed over natural log of x. And arrowing out, this says I'm taking the derivative of the f of x function I had, 0.57, and get negative 2.762. And all that's telling me is my slope of this function at x equals 0.57 is this value. And think about what that could help us with. It would tell me that my function is decreasing at x equals 0.57. And not only that, we know it's decreasing by about negative 2.762. So just make sure you're familiar with how to use the calculator when we get to more complicated examples. Finally, looking at the graph of a function f and its derivative f prime. And this last one is making connections between the graphs of a function and the graphs of its derivative. Because remember, given any function f, its derivative is also a function. So how we're going to take a look at this is to focus on the slopes of your f function. Because what we need to remember is the slope of f is the value, specifically the y value of f prime. That is my output. So if you look along this graph, well, there's going to be a few spots that stand out to us. Let's trace along the graph from the beginning to the end. And at the beginning, notice this function is increasing, it's moving up, which means I know I should get positive slope values. Really positive here, still positive, but getting less and less positive all the way. When I get to this point at the top, this maximum, what we should realize is this is a spot where my graph has flattened out, where if I had a tangent line, the slope would be 0. I have another one of those over here as well. In between those two spots, my graph starts decreasing. If I think about making tangent lines, they would have negative slopes, getting most negative around here, and then just returning to being slightly negative as I get closer to this relative minimum. Moving beyond that point, notice how the slopes turn back to being positive and get more and more positive. I know two spots where I, for sure, have my derivative value. These spots where my derivative was equal to 0. So I can make these 2 points on f prime of x my derivative. I know I have very positive values before this first root. I have negative values in the middle, and I have very positive values again afterwards, making something that, well, best way I can think to make this is with a parabola. That's the only function that fits where I go from having positive values, getting closer to 0, to negative values, and back to positive. It'll be a little bit tricky at first, but this is how we're going to get ourselves into making nice concrete connections between any function and its derivative by not only looking at derivative values, which we have been doing, but by also looking at their graphs. So now that you've finished this section, that completes Unit 2. Please make sure, review, and summarize your notes. Thank you for watching.